Okay, so hello everyone. Good evening, guys. Hope you're doing well. So today we are gonna study a new topic called thermodynamics. This thermodynamics is study of gases and heat. So in this part one of this thermodynamics, we are gonna study about some basic terms and some thermodynamic processes, and we will continue with quasi-static process and Carnot engine in part two. Okay, so let's get started. So first of all, we will have to look at some basic terms of thermodynamics as we are studying a new chapter about gases. So we must know what this chapter and about its terms. So the first term is system, surroundings and universe. So like if we have a flask or a test tube and we are going to study on it, then this only this test tube is our system and everything else except system would be surrounding, like the atmosphere around it, or if we have put a box near it, the box will also consist of surrounding, and system and surrounding combined would be our universe. Okay, so the system and surroundings are separated from each other with the help of a boundary. Like in this case, this boundary is made up of glass, which separates this liquid from mixing with the surrounding. Okay, so like this is just our day-to-day life example, but in this chapter we are going to study about gases and their systems. So our system would consist of a piston, and this wall could be of different types, like it would allow heat or may not allow heat transfer or matter transfer. So these boundary would be different and of different types, and we are going to study about the system, which is the gas present inside this piston. So there are three types of system. Okay, so the three types of system are open, closed and isolated. So let's look at them with on this black slide. So open, closed and isolated. So as the name suggests, this open system is the system. Okay, before that, the thing we are gonna discuss is about matter and energy transfer. Okay, so we are gonna look at matter and energy transfer on each of these system. So this open system, okay, we are gonna denote matter with M and energy with E. So this open system, closed system and isolated system. So this open system allows both matter transfer and energy transfer. But this closed system does not allow matter transfer but only allows energy transfer. The isolated system does not allow any exchange. So let us look at examples because this is very hard to understand. So we can say it like our jar placed on gas with heat being provided to it with no lid over it. So here it is water which is boiling. So boiling water can easily get into the surroundings as there is no boundary to protect it, while these three boundaries just protect the water from not going outside the container. Okay, so in the closed container case, what we are just gonna do, we are just gonna put lid over this. So now we have put a lid over this, and so now the matter cannot just transfer from this vessel water to outside. Okay, and the third type of system which is isolated, we can say it like a thermos flask or anything like that, which does not allow any of this. And you may have heard of, okay, refrigerator is also a good example because refrigerator does not allow anything to pass, not even matter, okay, and not also energy because refrigerator keeps itself full. Okay, so going back to system and surrounding, we get to know about thermodynamic equilibrium. So this is the highest form of equilibrium, and any body is in thermal equilibrium if it is in mechanical equilibrium, thermal equilibrium, and chemical equilibrium. Okay, so mechanical equilibrium means that it is rest, and the thermal equilibrium means that it has no temperature change, and chemical equilibrium means that it is not reacting with any substance. Next we have thermodynamic states. Okay, so we can see that system can just pass the energy by work and heat. So we are gonna study it about in the laws of thermodynamics. Okay, so the thermodynamic properties. Okay, so thermodynamic properties are, we can say, extensive and intensive. So extensive and intensive are different types of properties which can change or not change with respect to change in temperature, change in size, and some other states. So first of all, we need to learn what is a thermodynamic state. So a thermodynamic state is represented or is just a collection of pressures, where volume, temperature, density, viscosity, etc. at a certain stage. Like if this is a gas and this gas has expanded, so we can say V1, V2. So this is state 1 and state 2. Okay, so this is volume 1, this is volume 2, and volume 1 is less than volume 2. And also we can include pressure, temperature, density, viscosity, etc. Okay, so the thermodynamic states are also represented in graphical forms by different points on the graph. Like if this is a PV graph, then this may be state 1, state 2. Okay, so these thermodynamical properties are the properties which are intensive and extensive, and these are some examples of them. So these are the, you can say, data points in this thermodynamic properties which are get collected. Okay, so after this we are gonna look at work, heat. Okay, to get to know about zeroth law of thermodynamics. So as we can see in this basic terms, we have made work and heat. So we can see that the Q is heat and W is the work. So we can see in this system, delta U is the internal energy. Heat gives work. So as we give heat to the system does work. You can think of it like electric motor or a fan. So if we give electricity to the fan by switching, just flipping the switch on, we will see that the fan will do work by giving us air, or just setting the air, still air into motion. So which is our work in this case. Okay, so now we can see that the Q in minus Q out is Q, or it is also written as delta Q. Okay, Q and delta Q are simply the same things, and the work done, or the work output minus the work input, is equal to the delta work or change in work, as you can see here. Okay, so now moving on to the zeroth law of thermodynamics. This law of thermodynamics is also called the law of temperature. Okay, because with this we have invented temperature, like we can see. So this law says if there are three bodies A, B, and C, and let us we know that A and C are in thermal equilibrium. Okay, thermal only. We do not know about mechanical and chemical. Okay, we don't care about that. And A and B are also in thermal equilibrium, which means that B and C would be in thermal equilibrium. Okay, like we can see. And because B and C are in thermal equilibrium, and we know that A and B are in thermal equilibrium and A and C are in thermal equilibrium, you can see this is a triangle forming, and we know that all of these three things are in thermal equilibrium. Okay, so this is just the zeroth law. And well, you might not have heard of zeroth law, like everything starts with first, so first law of everything, while thermodynamics starts with zeroth law, because this zeroth law was discovered after the discovery of first law. But then when first law was discovered, after some years the scientists thought that this is incomplete, there should be something behind it, but what to give before first, so they named it zeroth law and the law of temperature, because the first law of thermodynamics include temperature, but they are not defined temperature till then. Okay, so first law of the thermodynamics state, or it is generally like a equation, while physics and chemistry differ by equation. Okay, by just a plus or negative sign. Okay, we'll look about that just a bit later. So now we can see that in, okay, so when heat Q is added to a system while the system does work W, the internal energy changes by the amount equal to Q minus W. So Q minus W is equal to U, and from here we can say work done. Okay, or simply the heat is equal to internal energy plus work done. Okay, so after that we know that this law of thermodynamics is the law of conservation of energy adapted from thermodynamic processes, and a simple formation of this law is the total energy of a system remains constant. Okay, as we can see, it is converted from one form to another, like from heat to work or work to heat. Okay, so now the thing is that the chemistry students, or the thing that we have learned in chemistry is that if the gas is done work, the gas gets tired, and so if this is a system, okay, this is a system. In chemistry we say that if heat is given to the system, we take it positive, because now the gas has become energetic and it has become positive. While if the gas does work or gives out heat, okay, we have given the gas work, let's say. Okay, so if the gas does work, the gas gets tired and we take it negative. Okay, while the physics thinks that the doer does positive work, so gas gets happy when it does work and should be taken positive. Okay, like if we give energy to the system by just removing out this weight by some small weight, we can see that the gas has done work or expanded. So in physics it would be taken as positive, while in chemistry it would be taken as negative. Okay, so now we can see that there are different processes. Okay, so there are different processes. So the processes are isothermal, isobaric, adiabatic, and isochoric. Okay, so we are gonna study at each of them. Okay, so now as we can see that for the derivation of work for all of these processes, we are gonna use some simple equations. The first equation is, you might have heard or written it in chemistry. See, delta Q is also equal to Q, so don't get over it. Okay, and delta U is equal to NCV delta T. Okay, so don't worry, we will prove it. Okay, you might have not heard it. Okay, and the fourth and the last equation is delta W is equal to integration of P dV. Okay, you might have known it. So now let's look at the first process, which is isochoric. So in this isochoric process, what do? We know that the volume is constant or V is constant. So we can say V equal to constant. Well, if V is constant, then the differentiation of it would be 0, or the change of volume would be 0. So V dV is equal to 0. So when the volume does not change, we can use the fourth equation, like the work done is equal to P dV, and we know that dV is equal to 0. So from there, we can see and say that, okay, integration of P times 0, and P anything times 0 is equal to 0. And we also know that delta Q is equal to delta U plus delta W, which is equal to 0. So U is equal to U, and we know that NC delta T is equal to delta U. Okay, but we are gonna write something CV instead of C, because this is for constant volume. Okay, so the graph or the PV graph for this case would be from A to B, a straight line. Okay, because volume is constant, so it is not going to go in the forward direction. Okay, so after this, what we are gonna do, we are gonna derive for isobaric processes in which the pressure is equal to constant, or delta P is equal to 0. See, we cannot say anything about the work. Okay, because the pressure is constant, so we cannot say the work done is equal to 0, but we can derive for the work. So we are gonna derive work from work done is equal to integration of P dV. We know that P is constant, so it will get outside of the integration, and we are gonna derive it from V1 to V2, so that we don't get constant. Okay, and at the integration of dV is equal to V. So we have P times V2 minus V1, change in volume. From here we can say that the work done is equal to P delta V. Okay, delta V is equal to change in volume. So from here we are gonna derive the heat. So delta Q is equal to delta U plus delta W. Okay, and we know that delta W is equal to change in P. Okay, so pressure times change in volume. So we can say it as, so we can say it as NCP delta T is equal to NCV delta T plus P delta V. What we have done, we have just used some of these equation. As we can see, we can just substitute delta Q to be NC delta T and delta U to be NCV delta T. Okay, so now we can see that from here delta Q is equal to NCP delta T. Okay, so this thing NCP delta T is because pressure is constant. This thing is substituted here. Okay, in place of delta Q. So after this, we have something called as Mayer's relation with a new constant terms named as Reynolds number. Okay, not the pen company Reynolds. So which is Cp minus Cv is equal to R. Okay, so to derive it, it is easier to derive using isobaric process, so we are going to do that. Okay, so for isobaric process, we have just derived that ncp delta T is equal to ncv delta T plus P delta V, and from here we know that PV is equal to nRT, and from here deriving this P delta V is equal to n R delta T. So what we have done, we have just done this thing. You should know this. We were given PV is equal to nRT. Just differentiate it with respect to volume. So P dV, okay, over dt is equal to n R, because these things are constant, dt over dt. We can see these dt's and dt's get cancelled. You can take anything else dt too, and we get d can be written as delta 2. So P delta V is equal to n R delta T. Okay, very easy to differentiate. Okay, so for isobaric process, pressure is also constant, so pressure has not get delta. Okay, so just substituting delta T and okay, and sorry, P delta V to this, we get ncp delta T is equal to ncv delta T plus nr delta T. So as you can see from here, something get cancelled, like n delta T and delta T, and we have Cp is equal to Cv plus R, or we can say it like that, Cp minus Cv is equal to R. Okay, here Cp is molar specific heat at constant pressure, and the delta Q required is the 1 degree rise of 1 mole when pressure is constant. Okay, so Cv is equal to delta Q Re required for 1 degree Celsius of 1 mole when volume constant. So Cp is always greater than Cv. Okay, next process is isothermal process. So now what we are gonna do, we are gonna make a, I think so we have not discussed how to make such processes, so we are going to discuss about adiabatic and isothermal. So isothermal process is the process in which the container is allowed to expand freely so that the temperature remains constant and no heats build up. So if we take a container of gas, okay, and just allow it to expand freely by just making a freely moving piston and allowing the piston to move freely by no brakes and no friction. So the gas does work when heat is provided to it and the temperature of the gas does not rise. So we can see it from here that we can also do this by just putting a water bath in this container, and in this constant temperature like 30 degrees Celsius maintains, and we provide delta Q slowly. So the heat should be provided slowly, otherwise the pressure would build up. Okay, so the work done, or delta W, is integration of P delta V. We have just done this many times and we are gonna do it again. Okay, so we also know that PV is equal to nRT. From here we can say that P is equal to nRT T by V. And we have done this so that because we know that the volume is changing, okay, and we know that for isothermal process temperature is constant. So because there is no change in temperature, we can just make a relation between P and V. This is P naught R. Okay, so now we have made a relation between P and V, so we can substitute the value of P by V. See, if we do this for a non-constant temperature process, what we would get is delta W is equal to, see, pressure, oh sorry, this number of moles, and the Reynolds number is constant, so it comes out of the integration, and we will be left with dV over V. Okay, and we know that anything integration, sorry, T is also constant, but if the temperature was not constant, this T would just remain in the integration, and we don't know the integration of temperature with respect to volume, as there is no relation. But because we know that temperature is constant for this process, we can easily take the T out of the integration. Okay, so integration of 1 over V or dV over V is ln V. Okay, this is just basic integration. So from here we can say delta W is equal to N R T ln, and we have done this integration, okay, from, let us say, V final, V initial to V final. So this is ln V final minus ln V initial. Okay, we have put the limits to, and we know that the ln A minus ln B is equal to ln A over B, so we can write it as ln V final over V initial. Okay, so after this we know that the internal energy change is equal to 0, which means delta T is equal to 0, because we know delta T is equal to 0. Then we can see, okay, so from we know delta T is equal to 0. Okay, because delta T is equal to 0, let me write down here. Delta U is also equal to the change in internal energy, because everything is converted into work. Okay, so we know that delta U is equal to NCV delta T. So delta T is equal to 0, which means the internal energy equal to 0. I've just proved it. Okay, so now because we know that internal energy change is equal to 0, so delta Q is equal to 0 plus delta W, which is just delta U, but in this case delta U is equal to 0. Okay, so we can write delta Q is equal to delta W, and because we know that, we can say delta Q is equal to NC delta T. Okay, so from here the C would become infinite, and the delta T is 0. So infinity is 0 is equal to a finite number which we do not know. Okay, so how can we say C is infinity? So from this thing we can say, from here, let me just erase this container for space. Okay, so we know from this equation that C is equal to delta Q over N times 0, and anything over 0 is equal to infinity. So C is infinite and delta T is 0, so we know that this is a finite number which we do not know, delta Q or the heat required. Okay, so the graph for this, the PV graph is something like this. In this case, the isothermal process is the blue colored one. Okay, so this graph is also called as rectangular hyperbola. You will learn it in math in conic sections about hyperbola. Okay, so after this we have adiabatic process, in which we know that the change in heat is zero, or delta Q is equal to zero. Okay, so we know that delta Q is equal to NC delta T. Okay, so we know that delta Q is equal to 0. N cannot be 0. So from here we can see C delta T is equal to 0. So now we have a doubt how to achieve this process. So we achieve this process by just making adiabatic walls. Okay, thermally insulated walls. So this is isolated system. The isothermal was closed system because there was exchange in energy. But in this case we have no exchange in energy and everything just builds up. Okay, so it is also, these walls are also known as diathermic walls. Okay, so first option is to create setup like this. The second option is to just do the process very quickly or very fast, so that the heat does not get time to escape, and so the heat does not escape. Okay, so heat actually takes time to move. Okay, so example as tire bursting, because tire burst very fast, and sudden compression of piston also leads to this. Okay, so work done for this, delta W is equal to integration PdV, and using PV to the power gamma is equal to constant. Okay, where gamma is some constant. Okay, so K is also some constant. We can say from here that P1 V1 to the power gamma is equal to P2 V to the power gamma. From here we can say the delta W is equal to integration of V1 to V initial to V final, K over V to the power gamma dV. Okay, and from here we can just see that K is constant, so it will come out of the integration, and we can write it as V to the power minus gamma dV. And we know that integration of x to the power a is equal to x to the power a plus 1 divided by a plus 1. So the same thing will happen here, and we will get a very bad or very lengthy result. Okay, which is k v to the power minus gamma plus 1 divided by minus gamma plus 1 from v initial. Okay, let's put the limit to v final minus v initial to the power of minus gamma plus 1. Okay, and now just doing rearranging some terms to get some good looking result. What we can do is write the result that we got. Okay, let us look at the result one more time. K times v final minus v initial, K times v final to the power minus gamma plus 1 minus k times v initial to the power minus gamma plus 1, and 1 minus gamma just sits outside. Okay, so just rearranging this thing once again and substituting the value of k again, we get k is equal to p2 v2 to the power gamma, or p final v final to the power gamma times v2, or v final to the power minus gamma plus 1, minus p initial v initial to the power gamma v initial to the power minus gamma plus 1, and this whole thing divided by 1 minus gamma. Okay, from here we can write delta of the work done is equal to p2 v2 minus p1 v1, just changing p final to p2 and p initial to p1. We can say delta work done is equal to 1 minus 1. From here we can say delta w is equal to nr t2 minus t1 divided by 1 minus gamma. Okay, so the last process is free expansion, in which there is no obstruction. Okay, also the adiabatic process has a sudden decrease or a exponential or ln graph. Okay, while isothermal is much more this adiabatic is much more steady than isothermal. The next process is free expansion. In this free expansion there is no obstruction of the expansion, so the gas has to do no work at all to expand. Okay, like we can see, so we know delta q is equal to delta u plus delta w, and 0 delta u is equal to 0. From here we can say delta t is also equal to 0. Okay, so after this is Poisson's ratio, which we will discuss in part 2. Thanks for watching and see you soon in the next video. Thanks and bye bye.